welcome back. I hope your break was fantastic. We are going to jump right in with one of my favorite units of the year, and that is getting into trig identities and verifying trig identities. We've done a little bit of work with solving trig equations, but now we're going to get down into more of the simplification process first, and then eventually we'll get to verifying identities. For today, it's important that we take a few minutes and sort of remember what we have in our arsenal so far. So we have four really basic identities that we've kind of used without even realizing that we're using them. The first are what we call cofunctions. And our cofunction identities are identities that we talked about early on with our trig processes. And we looked at if you took the sine of 90 minus theta, it ended up being the same as cosine of theta. And we proved that by looking at a right triangle, labeling one of the acute angles theta and the other angle 90 minus theta, and then going through and finding the sine and cosine of them and showing that they ended up being the same in that triangle. So we've kind of seen these cofunction identities already. We've talked a lot about reciprocal identities, and that's what you'll see next. And we talked a lot about, we've talked about how if we wanted to find, the reciprocal of sine, we know that's cosecant. The reciprocal of cosine is secant. We have these written out in a more algebraic fashion. So literally writing the reciprocal of cosecant would be 1 over cosecant, and another way to write that is sine. So that's what our reciprocal identities are. Next, we've talked about our quotient identities, and that was really early on in this process we looked at on the unit circle. Another way to kind of talk about tangent was not just the y-coordinate divided by the x-coordinate, but it was also sine divided by cosine. And then we also had cotangent in there as well. And then finally, the Pythagorean identities. We talked about those in the last unit. And that, again, directly related back to this idea of a right triangle. We said that in a right triangle, a squared plus c squared equals a squared plus b squared equals c squared. Well, with our right triangles on the unit circle, very specifically, we could say that a would be sine, b is cosine, and c is always 1. So we ended up with these three Pythagorean identities, and we even went a little bit further and kind of morphed each of those into two other forms. We've talked a little bit about the even and odd identities. And that was just kind of knowing that the sine of negative theta is the same as the negative sine of theta, and so on. So they're just ways that we can sort of rewrite something if we see it. So what we're going to be doing with all of that information is taking an expression that has trig functions in it and finding a way to make that complex expression look simpler. Now, before we get started, some ground rules. What we'd really like to do, if at all possible, is come up with a simplified version of the expression that has just one trig function. If that's not possible, we want to get the fewest number of trig functions that we can. Okay, so that's one way that we know we can simplify. We try to get any squared functions rewritten in another way if possible. We try to really get it to sines and cosines if we can. These are all sort of things that as you start to simplify, you'll begin to get a feel for. And this is the first step in a process that we're going to continue to build on. For right now, we don't always necessarily know, have we simplified it enough? That's always kind of the question I get. How do I know when I'm done? Well, you look for other substitutions. If you can make some more substitutions, then you try that and you see if it makes our expression any simpler. If it makes it more complicated, then you know what, you're done. So to start out a process, what I do is I look at each function that I'm given. And here I can see I'm multiplying cosine times secant. So I ask myself, are there ways to rewrite cosine or secant? And I really want to focus on, if I can, this is a really good strategy, writing things in terms of sine and cosine. I like sine and cosine because they show up in a lot of our identities. So I'm going to try to come up with a way to turn things into sines and cosines. So I might not want to try to find a way to rewrite cosine, but what I might want to do is try to find a way to rewrite secant. So what I would do is look up at my all of my different identities. And I ask myself, you know, how can I rewrite secant? And I start to look at all the different ways I can rewrite secant. Well, I could rewrite secant as the cosecant of 90 minus theta. Okay, it doesn't really help me a lot in this situation. That's actually more complicated. If I look at my reciprocal identities, I can rewrite secant as 1 over cosine. Now that's interesting for a lot of reasons. The first is that it rewrites it in terms of cosine, which I see in my expression. So here's what I'm going to do. I'm going to rewrite my expression, keeping cosine of x as is, but writing secant of x as 1 over cosine of x. Now, what I like to do, and you guys have heard me say this year, whenever I see one fraction in an expression, I make everything a fraction. So I'm going to write cosine of x as cosine of x over 1. So really what I'm seeing here is a multiplication of fractions. I've got cosine of x times 1 over cosine of x. So when I multiply those together, I'm going to get cosine of x over cosine of x. And then really beautifully, that just becomes 1. All right, I'm going to try to move through these next ones a little bit faster. And if you get confused, please make a note and feel free to ask in class. So tangent squared of x times cosine squared of x. Once again, I kind of like that I already see a cosine in there, but what I'm going to look at is there another way I can rewrite tangent? And it's specifically tangent squared. So initially, a lot of times we want to look at our Pythagorean identities when we're talking about any squared functions. Tangent squared could be written as tangent squared of theta equals secant squared of theta minus 1. While that's interesting, it doesn't really make things any less complicated. It tends to actually make it a little more complicated, especially with what I have written there. But what I want you to know is with all of these, I can use the squared versions of these. In other words, if I look here at cosecant, I could really say cosecant squared is the same as 1 over sine squared. Okay, so the squared versions of all of these will work as well. What you have to be careful with is that with the Pythagorean identities, you can't use the non-squared version of this. In other words, sine of theta plus cosine of theta does not equal 1. All right, so you can square something, but you can't take the squared away in the Pythagorean identities. So what I want to point out here is that over here we've got our tangent. So I could write that as tangent squared of theta equals sine squared theta over cosine squared theta. And then I can make that substitution. So let me come back down to my problem here, and I'm going to write tangent squared as sine squared over cosine squared. And see what that does for me. So I'm multiplying that by cosine squared. Now remember, because I see one fraction in my expression, I'm going to make everything a fraction. I hope that you're all noticing right away, look at that, we've got a giant 1. So because of that giant 1, I can rewrite this whole expression as just sine squared over 1, which I can just leave as sine squared. I'm not going to flip back and forth to the identities, but hopefully you have either a copy of that printed out in front of you, or you can look at it electronically. And again, I'm going to try to move through these rather quickly. So 1 minus sine squared over cosine squared. So what I notice about that that's quite interesting is that I have 1 minus a squared trig function. That should set off alarm bells for you, because 1 minus sine squared, according to our Pythagorean identities, is cosine squared. So what I know is that I can replace 1 minus cosine squared, or 1 minus sine squared with cosine squared. So really what I end up with is cosine squared over, I'm not going to change this at all, cosine squared. And then again, beautifully, that simplifies to just be 1. So I know that this expression, another way to write it, is 1. This one tends to give people a little bit of trouble, but what I want you to remember is that pi over 2 is just 90. So what if I were to rewrite this as sine of x times secant of 90 minus x? Now I hope that this you recognize as being one of your cofunctions. Go look at the cofunctions. Secant of 90 minus x is just cosecant. Now, that's interesting. It's simplified, but I think we can go further because I still see two trig functions. I still see something that's not written as a sine or a cosine. So now what I'm going to do is think about how else can I write cosecant? And if I go look at, I'm going to write over here, we used cofunctions to go from here to here. And then I'm going to use my reciprocal functions next. because I know that the cosecant of x can be rewritten as 1 over the sine of x. So now if I rewrite this, I've got sine of x, let me not forget my equal signs here, sine of x times, instead of cosecant, I'm going to write it as 1 over sine of x. And then once again, when I have one fraction in my expression, I'm going to make everything a fraction. And then I see I'm multiplying and I end up with sine over sine, which once again simplifies to just be 1. So this expression can be written as just 1. Now we start to get into some really interesting things where we can start applying our algebra skills. I have the product of two binomials. Now, there's a lot of ways that you can look at this. Maybe some of you are noticing that this actually represents a difference of squares and you see a shorter way to do this. But what I want to be able to do is maybe multiply this out. So if I were to multiply this out, I would have to multiply my 4 terms. Okay, so I'm going to get secant squared of x minus secant of x times tangent of x, and then plus secant of x times tangent of x, and then minus tangent squared. Now, as far as the order of these two things, remember, it does not matter which order I write them because I'm multiplying them. 2 times 3 is the same as 3 times 2, so secant times tangent is the same as tangent times secant. But what's really important here is that I have negative secant tangent plus secant tangent. Those are going to end up being just 0. So then what I have is secant squared minus tangent squared. Now, maybe that's as good as we can get. I would encourage you to double check. So go back and look at your Pythagorean identities and let's see if there's another substitution we can make there. So what you probably notice is that your Pythagorean identities have 1 plus tangent squared equal to secant squared. We have other varieties that we've looked at in the past. If we subtract tangent squared from both sides here, I'm going to have 1 equals secant squared of x minus tangent squared of x. That's one way we can think of this. Here's another way. Let's imagine maybe you don't realize that you can rewrite that expression, but what you do know is that another way to write secant squared is 1 plus tangent of x. So instead of secant squared here, what if I write that? What if I write 1 plus tangent squared, and then I still have this minus tangent squared? Now I've got something that I can really easily simplify because tangent squared minus tangent squared is just going to be 0. So once again, I get something that simplifies to be 1. I know it seems like it, but they don't always simplify to 1. This problem tends to give a lot of people trouble because you probably intuitively want to write, oh, that's just sine squared plus cosine squared. No. What this is really saying is you have to take sine of x minus cosine of x and multiply it by itself. That's what that expression is saying. So I'm going to do like what I did in part E and multiply that out. So I'm going to get sine squared minus sine of x times cosine of x, and minus sine of x times cosine of x again, and then plus cosine squared. Remember, that's just me multiplying my 4 terms. In the middle here, I've got negative 1 sine of x cosine of x minus 1 sine of x cosine of x. So what I get there is minus 2 sine of x times, not sine squared, just minus 2 sine of x times cosine of x, and then plus cosine squared. Now, some of you may be thinking, okay, well, am I done? Because that looks not any more simplified than what I started with originally. What I would encourage you to remember is that just like with multiplication, I can add and subtract, I can add terms in any order. In other words, what if I did this? What if I rearrange my terms and I put this plus cosine squared up with the sine squared? Now, this right here, sine squared plus cosine squared, you should recognize this. Once we do a lot of these, you're going to start recognizing that sine squared plus cosine squared shows up a lot. And when it does, we know that that can just be rewritten as 1 because of our Pythagorean identities. And then what I have is 1 minus 2 sine of x cosine of x. Now, at this point, you can ask yourself, can I rewrite this in another way? Is there anything I know that I can rewrite 2 sine of x cosine of x as? And there's not. remember I said at the beginning, we want to try to write things in terms of sine and cosine. We've done that here. Everything's in terms of sine and cosine. We don't have any secants or cosecants or tangents or cotangents. So we can't change anything into sine and cosine because it's already done. We can't really write 1 in any other version other than to make it more complicated. So at this point, we're really as simplified as we can get. And I know that's a little unsatisfying probably for some of you, but that is as simplified as we can make this expression. So the lesson from that previous example is that you aren't always going to be able to get it to simplify to a single term. Keep that in mind. All right, next up, we've got a lot going on here. So I want to highlight some things here. This guy is our first term because we see that they're being multiplied together. This is our second term, and those two things are being subtracted. So what I'm going to do is take this really slowly, one piece at a time. I'm going to start by looking at cosine of negative w. I do not like having a negative sign in front of my angle, so I want to find a way to rewrite that. So go take a look at your even and odd identities, and what you'll notice is that the cosine of negative w is just exactly the same as the cosine of w. All right, so we've taken care of that piece. How about cotangent of w? Remember, I like to write things in terms of sine and cosine whenever I can. It tends to make things sort of the same language. You can think of it that way. So when I think about cotangent, lots of ways that I can rewrite that. But what I'm going to gravitate towards in order to get that into sine and cosine is my quotient identity, which says that cotangent is really the same as cosine over sine. Now, because I have one fraction, I'm going to make that all a fraction. Now, that's my first term, and I'm multiplying those two things together. I'm going to just finish that really quickly here. So cosine times cosine is cosine squared over sine, not x, sorry, watch your variables there. Cosine squared of w over sine of w. Now, next up, I've got this minus sine of negative w. So I want to think about how can I rewrite sine of negative w. So sine of negative w is the same thing as negative sine of w. And again, that comes right from your even and odd identities. So now I see that I'm subtracting a negative. So that's really the same thing as saying adding. So I've got plus sine of w. Now, once again, because I have one fraction, I'm going to make everything a fraction. Now, maybe you're looking at this and you're like, well, that doesn't look a whole lot better, Mrs. Kopp. Well, you'd be right, but there's more we can do because I'm adding fractions together. In order to add two fractions together, I hope you remember, all you need is a common denominator. So what I've got to do is get a common denominator, which means this second fraction, I'm going to have to multiply by sine over sine. Now, what that does for me is it gives me cosine squared of w over sine of w plus, now I have sine squared of w over sine of w. Now I have a common denominator. So what's really great about that is I can go ahead and add those fractions together. So I'm going to get something over the sine of w. And that something is cosine squared plus sine squared. I'm going to sound like a broken record, but I hope you recognize this. Okay, same thing as saying sine squared plus cosine squared. That's just 1. So what I get here is 1 over the sine of w. Now, while that's great, it's simplified, we have it down to one term, I don't generally like having a fraction where the only trig function is in the denominator. So I'm going to look back at all of my possibilities here, and if I search through my reciprocal functions, my reciprocal identities, I'll find that 1 over sine is just the same thing as cosecant of w. So that entire expression at the beginning can simplify to just be cosecant of w. All right, next up, another multiplication needs to happen here. And the reason I say that, we're using some algebra skills here, okay? So I noticed that I have something being multiplied times a binomial, and I'd like to maybe multiply that out and see if that leads me to something else. So I'm going to distribute that sine of x. What that does is it gives me sine of x times sine of x, which is just sine squared, minus sine of x times cosecant of x. Well, the sine squared, that's kind of nice, okay? But the sine of x times cosecant of x, again, I'm recognizing that I want to turn everything into sines and cosines if I can. So this cosecant of x, if you look at your reciprocal functions, cosecant of x can be written as 1 over sine of x. So that's exactly what I'm going to do. I have sine squared of x, I'm going to leave that be for the time being, minus sine of x times 1 over sine of x. Now, because I have one fraction, I'm going to make everything a fraction temporarily, okay? So, looking at multiplying first, I need to take care of this term right here. And again, I hope you guys recognize that there is a giant 1 right here. So what I end up with is sine squared of x over 1 minus 1. Now, I don't necessarily have to write this over 1 anymore. What I really have is sine squared of x minus 1. Now, you could look at your Pythagorean identities, but what you'll notice on the Pythagorean identities is that you have, so sine squared plus cosine squared equals 1. If I wanted to get this to be sine squared of x minus 1, I'd have to manipulate a little bit. But here's what else I can do. Minus 1, so this is 1, right? Another way to write 1 is sine squared plus cosine squared. So what if I try that? Sine squared of x minus 1, which is really sine squared plus cosine squared. Okay, what does that do for us? Well, we end up with sine squared minus sine squared minus cosine squared. Well, that's kind of nice because that sine squared minus sine squared minus sine squared is just 0. So what I end up with is negative cosine squared, which is a little more simplified than what we had up here. Honestly, I would probably take either one of those, but I just wanted to show you that there is another way to write that. Okay, we're going to get into a couple more strategies here, but what I want you to do is pause the video and try factoring these 3 expressions here. Okay, so take a minute, factor those 3 expressions, come back, and we'll just double check what you have. So this is some pretty basic factoring, and I would hope that you would recognize that in part A, you only have a greatest common factor. Part B is a difference of squares, and part C is just a regular basic old factoring for a trinomial. Now, we've done a lot with factoring in our solving equations unit, and we're going to continue to look at those things in this unit. So to start with, you might need to, as I showed you in a lot of our in-class discussions, think about how you can rewrite each function and do a substitution. So maybe in this first example, maybe I make sine of x, a, cosine of x, b, and then what happens when I rewrite this? So I would have anywhere I see sine, I'm going to write a. Anywhere I see cosine, I'm going to write b, so that'd be b squared, minus a. And that's a little bit more, I think, easier for you guys to factor, because what you should notice is that you have a greatest common factor of a. So I could rewrite that as a times b squared minus 1. Now, that could even factor a little bit more, right? This could be a times b minus 1 times b plus 1, because we really have a difference of squares with b squared minus 1. Now, the key is you've got to go back and rewrite it with your trig functions. So this guy is then going to become, I'm going to kind of move in a kind of awkward direction here. A is sine of x, so I'd have sine of x times cosine of x is b minus 1 times cosine of x plus 1. This would be how I could factor that original expression. Now, part B is just straight up a difference of squares. If you need to, do a substitution and call secant of x, a again and factor it like that, you can. But I would hope that you recognize that, hey, this is just a difference of squares. So secant of x minus 1 times secant of x plus 1 would be a really easy way to factor that. And then again, if you need to do a substitution where you call maybe tangent, you call t. So I'd have t squared minus t minus 20. I can factor that to be t minus 5 times t plus 4. Well, if tangent is being replaced by t, we have to go back to our original expression using tangent. So I could write that as tangent minus 5 times tangent plus 4. Don't forget the x's there. So tangent of x minus 5 and tangent of x plus 4. So lots of ways that you can think about how to factor with trig expressions, but don't forget that you can use the idea of substitution. So that's an important strategy to use when you might have to then factor some trig expressions. So we did a little bit already with common denominators, but let's just take that a little bit further. So in this first expression, I'm trying to add these two fractions together. I need to have a common denominator in order to do so. Well, it looks like I'm going to have to multiply this first expression by the cosine of x and the second expression by the sine of x over sine of x, and then I'll have a common denominator. So what does that turn into? Well, I've got cosine of x over sine of x cosine of x plus, and then I'll have something kind of weird looking here. I'm going to have, if I think of this as then being distributed, I'm going to have sine of x cosine of x plus sine of x all over cosine of x times sine of x. My denominator is the same because cosine times sine is the same as sine times cosine. Remember, the order doesn't matter when we're multiplying. So I can combine these two fractions into one fraction with the same denominator. And what I get is cosine of x plus sine of x times cosine of x plus sine of x. Now be really careful here because some of you are like, oh, I see cosine squared plus sine squared is 1, Mrs. Kopp, so cosine of x plus sine of x must be 1. Remember, with Pythagorean identities, they have to be exactly that. So cosine squared plus sine squared is 1, but not the square root of that. You have to have the squareds. So I really can't do much else with that. I just wanted to be able to combine those two fractions, and I did so. Now, this one gets kind of interesting. So I'm going to actually play around with the denominators a little bit before I try to find a common denominator. So I'm going to leave 1 plus cosine of x alone for a minute because there's no squareds in there. It's already written in terms of sine or cosine. There's not a whole lot I can do with that expression. But what I do see is that sine squared. Remember, we talked about this in a previous unit. Sine squared plus cosine squared equals 1. Well, that means that sine squared is really 1 minus cosine squared, okay? If I subtract cosine squared from both sides, that's what I get. So instead of sine squared right here, I'm going to write it as 1 minus cosine squared. Now, you might be thinking, well, that just made it more difficult. Well, kind of, because what I notice next is that this is a difference of squares. So what if, before I find a common denominator, I do a little factoring? Okay, so leave the first fraction as is for a minute. But in this second fraction, what if I factor the denominator as a difference of squares? Okay, that's kind of nice because now I see that both fractions already have 1 plus cosine of x as a factor. So that means that all I have to do is multiply this first fraction by 1 minus cosine of x over 1 minus cosine of x. And when I do so, now I've got a common denominator. My common denominator is 1 minus cosine of x times 1 plus cosine of x. In my numerator, so 1 times 1 minus cosine of x, so that's just 1 minus cosine of x, plus 1. All right, well, that's getting a little bit better. So now I've got 1 plus 1 is 2 minus cosine of x. Why do I keep wanting to dot the cosine of x? Over, now I'm going to go ahead and write it as 1 minus cosine of x times 1 plus cosine of x, but you could change that back to the 1 minus cosine squared of x. Either one would be fine. The idea is I'm just trying to write these two fractions as a single fraction, and I've been able to do that here. All right, what I'd like you to try to do is see if you can work through and simplify these two expressions. So take a few minutes, pause the video, see what you can come up with, and then come back and check your answer with what I have. Okay, if you want to take a little bit of a closer look at these, you can pause the video and sort of check your answers. I tried to show every step along the way, but we're going to go ahead and look at the next set of problems. All right, I want you to try to figure out C. So pause the video again, see if you can come up with a way to rewrite that, and then come back and check your work. So that one was pretty quick if you use your Pythagorean identity and reciprocal identity. All right, let's talk about D. I've got a little hint there for you. We want to set it up so that we can factor because right now we can't. And we did some like this in our solving equations unit as well. My suggestion would be start by using the Pythagorean identity to rewrite cosecant squared and then see where that leads you. So go ahead and pause the video, see if you can find a way to factor this, and then come back and check your answer. So all I wanted you to do there was just find a way to factor. Hopefully you were able to do so. Go ahead and check your work, and let's go ahead and move on. So on E, I want you to try to find some common denominators and try to add these two fractions together. Your only goal here is to try to add the two fractions to make one fraction and simplify it as much as you can. So pause the video and try it and come back and check your answer when you're done. The key to this one was not only getting your fractions to be combined to be a single fraction, but was recognizing that sine squared plus cosine squared showed up in your expression, and that can be rewritten as 1. And once you do that, then you have this giant 1 because you have the same factor in the numerator and the denominator, which allows you to simplify that fraction even more to get it down to something that is a single term. All right, last one. So I want you to try to simplify this fraction as much as you can. It might not be that much. The key to this is going to be factoring. So go ahead and pause the video, try it, and come back when you're done to check your answer. Again, this might not feel very satisfying in that it's not a whole lot more simplified. We just got rid of a giant 1, that's all. Recognizing that your denominator was a difference of squares was really key here. Factoring that difference of squares and then finding a giant 1 was how you were able to then simplify that expression. All right, so a couple things to take away from this. You want to try to simplify by getting rid of any giant 1s, by combining fractions together whenever possible, either through multiplication or through getting common denominators and adding or subtracting. You want to try to get it to the least number of trig functions as possible, ideally, if you can, 1. And we always want to try to write things in terms of sine and cosine if possible. So those are some hints and strategies that you can think about as you're working through simplifying these expressions. I'm sure you'll have lots of questions, and we'll talk about those the next time we meet.